Welcome to our deep dive into the Stern-Brocot tree. I know as a number theory student, this is probably right up your alley, but today we're going to uncover some of its hidden depths and explore connections you might not expect.
It's true, the Stern-Brocot tree often gets relegated to kind of a curious footnote in number theory courses, but it truly is a mathematical gem with connections to a surprising range of topics.
Exactly. So for anyone just tuning in, let's start with a quick refresher. The Stern-Brocot tree is an infinite binary tree that contains every single positive rational number exactly once. Pretty cool, huh?
Absolutely, and what makes it even more fascinating is the way it's constructed. It all starts with the fractions 0, 1, and 10 as our boundaries.
Wait, 10. Isn't that undefined?
You're right, it is, but for our purposes, we're going to think of it as representing infinity, serving as a conceptual boundary for the tree.
Interesting. So how do we go from these boundaries to generating all the rational numbers?
Through a simple operation called the mediant. If you have two fractions ab and cd, their median is a plus c, b plus d. We add the numerators and the denominators.
Okay, so for example, the mediant of 12 and 13 would be 25.
Precisely. And this mediant operation is the key to building the entire tree. We start with our boundaries, or 1 and 10, find their mediant, which is 11, and place it between them. Then we continue taking medians, generating new entries, and branching out the tree.
So 11 becomes a new middle, and we find the medians of its neighbors 0, 1, and 11, giving us 12 and 21, and so on.
Exactly. It's a beautifully recursive process that generates every single rational number in a very specific order.
Okay, I see how the tree is built, but what makes this arrangement so special? Why not just list all the rational numbers?
What's fascinating about the Stern-Brocot tree is that it's not just a list. Its structure encodes deep mathematical relationships. For example, it has this remarkable property called the best rational approximation.
I'm intrigued. What does that mean?
Imagine you're trying to approximate an irrational number, like pi, using a rational number. You want a fraction that's as close to pi as possible, but you also want to keep the denominator relatively small.
Right, because with a huge denominator, we could get arbitrarily close, but that's not very practical.
Exactly. And that's where the median operation and the structure of the Stern-Brocot tree become incredibly useful. The tree essentially gives us a roadmap for finding these best rational approximations.
Could you give me an example?
Absolutely. Let's consider the square root of 2. It's not a rational number, so it won't be found directly in the tree. But we can use the tree to find rational numbers that get incredibly close to it.
So how do we do that?
We start at the root of the tree, 11, and compare it to the square root of 2. Since the square root of 2 is larger than 11, we move to the right branch of the tree. We then compare the square root of 2 to the next number on that branch and keep choosing the branch that keeps us closest to the square root of 2 without going over.
So we're essentially navigating the tree, getting closer and closer to the square root of 2 with each step.
Precisely. And the further we go down the tree, the more accurate our rational approximations become. It's a powerful way to visualize how we can approach irrational numbers using rational ones.
That's really cool. So the Stern-Brocot tree isn't just a list of rationals, it's a tool for approximating irrationals as well.
It is. And this is just one of its many surprising applications. But I think we should pause here and let our listener absorb this much before we move on to some even more unexpected connections.
That sounds good to me. What are your initial thoughts on the Stern-Brocot tree so far?
For me, it's the elegance of the median operation that always stands out. It's such a simple idea, yet it leads to this incredibly rich and powerful structure.
I agree, and the fact that this simple structure can be used to approximate irrational numbers so effectively is just mind-blowing.
It is. And it hints at the deep connections the Stern-Brocot tree has to other areas of mathematics, connections we'll delve into in the next part of our deep dive.
Okay, so we've established that the Stern-Brocot tree is this amazing map of the rational numbers and a tool for approaching irrationals. But you mentioned there are even deeper connections to explore. Where do we go from here?
Well, prepare to be surprised because we're about to venture into the realms of geometry and trigonometry.
Geometry and trigonometry. I have to admit I'm not seeing the connection yet.
It's not immediately obvious, but trust me, the Stern-Brocot tree has surprising links to these areas. Let's start with Pythagorean triples. As a number theory student, you're familiar with these. Sets of 3 integers that satisfy the Pythagorean theorem.
Of course, like 3, 4, and 5. But how on earth does the Stern-Brocot tree relate to these?
The key lies in something called stereographic projection. Imagine a sphere and a plane cutting through it. Stereographic projection allows us to map points from the sphere onto that plane.
So we're taking points from a curved surface and flattening them onto a plane.
Exactly. Now imagine we focus on the unit circle on that plane, the circle with radius 1. When we use stereographic projection to map points from the sphere onto this unit circle, something fascinating happens. The rational points on the unit circle, those with rational coordinates, correspond to Pythagorean triples.
Hold on. Are you saying that if I take a rational point on the unit circle, its coordinates can be used to form a Pythagorean triple?
Precisely, and here's where the Stern-Brocot tree comes in. If we project the entire tree onto the unit circle using this stereographic projection, we get a beautiful visual representation of this connection. The points from the tree map onto a set of points on the circle that give us Pythagorean triples.
So by projecting this tree of rational numbers, we end up with points that represent Pythagorean triples. That's pretty wild.
It is, and what's even more remarkable is that the tree's structure preserves a meaningful order. The triples corresponding to more acute triangles cluster together separate from those representing less acute triangles. It's like the tree is organizing these triples based on their geometric properties.
It's amazing. I never would have guessed that a structure built from fractions could have such a deep connection to geometry.
It's a testament to the hidden depths of the Stern-Brocot tree. And believe it or not, this is just the tip of the iceberg. We can take this geometric connection even further and link it to trigonometry.
Trigonometry. Okay, now you're really blowing my mind. I'm all ears.
Remember how each point on the unit circle can be represented by an angle? Well, the position of a projective point from the Stern-Brocot tree on this circle corresponds to a specific angle. And this angle, along with the rational coordinates of the point, can be used to approximate trigonometric functions.
Wait, so you're telling me we can use this tree to approximate sine, cosine, and tangent? How does that even work?
Think about it this way. The coordinates of a point on the unit circle are essentially the cosine and sine of the corresponding angle. So by projecting the Stern-Brocot tree and finding the point that corresponds to a particular angle, we can approximate its cosine and sine using the rational coordinates of that point.
So we're essentially finding a rational point on the circle that's close to the angle we're interested in and using its coordinates as approximations for the trigonometric functions.
Exactly. It's another incredible example of how the Stern-Brocot tree, this seemingly simple arrangement of fractions, can be used to approximate values in unexpected areas like trigonometry.
This is incredible. We've gone from fractions to geometry to trigonometry, all thanks to this one tree. It's like a hidden code that unlocks all sorts of mathematical secrets.
It really is. It highlights the interconnectedness of mathematics and the power of simple yet profound ideas. But I think we need to pause here and let our listener process this much before we wrap up with some final insights in the last part of our deep dive.
That sounds like a good plan. I'm still trying to wrap my head around how this tree connects to so many different concepts.
It's a lot to take in, I agree, but it's this very richness and depth that makes the Stern-Brocot tree such a fascinating object of study.
Okay, I'm still reeling from those connections to geometry and trigonometry. It's incredible how the Stern-Brocot tree, which starts with simple fractions, can lead us to these seemingly unrelated areas.
It is a testament to the interconnectedness of mathematics, isn't it? And these connections aren't just theoretical curiosities, they have practical implications as well.
Really, in what way?
We'll consider the best rational approximation property we discussed earlier. This feature of the Stern-Brocot tree is actually utilized in fields like engineering, particularly in gear design. You see, gear ratios often need to approximate specific values, but the number of teeth on gears needs to be an integer.
So the Stern-Brocot tree helps engineers find the most efficient gear ratios with manageable numbers of teeth.
Precisely. It allows them to find the best rational approximation for the desired ratio, ensuring the gears mesh smoothly and efficiently.
That's fascinating. So this seemingly abstract mathematical structure has tangible real-world applications.
Absolutely, and its potential applications continue to expand. Researchers are investigating its use in areas like computer science, particularly in algorithms for data compression and searching. The tree structure lends itself well to efficient sorting and retrieval of information.
So the Stern-Brocot tree is not just a beautiful mathematical object, it's a powerful tool with practical applications.
Exactly, and what's even more exciting is that there's still so much we don't know about it. There are open questions and conjectures surrounding the Stern-Brocot tree that mathematicians are still grappling with today.
So even after centuries of study, this tree still holds mysteries waiting to be unlocked.
It does. For example, mathematicians are exploring its connections to music theory, particularly in the way musical intervals can be represented as ratios. There are also intriguing links to the study of chaotic systems, where the tree's structure seems to capture some of the complex patterns that emerge.
Wow, the more we delve into the Stern-Brocot tree, the more fascinating it becomes. It's like a gateway to a whole universe of mathematical exploration.
I couldn't agree more, and for a number theory student like yourself, it's a treasure trove of ideas and connections waiting to be explored.
Absolutely. This deep dive has definitely sparked a desire in me to delve deeper into the Stern-Brocot tree. I
Ah.
can't wait to see where it leads me.
Well, as you continue your exploration, I'll leave you with this thought-provoking question. How might the Stern-Brocot tree be used to visualize and explore other mathematical concepts? What other hidden connections and applications might it hold? The possibilities are truly endless.
That's a fantastic question, and one that I'm eager to start investigating. This deep dive has been an incredible journey, opening my eyes to the beauty, power, and unexpected connections woven into this remarkable mathematical structure. Thanks for guiding me through it.
It's been my pleasure. Remember, the journey of mathematical discovery is never ending. There's always more to learn and explore, and the Stern-Brocot tree is a perfect example of that. Keep seeking, keep questioning, and who knows what amazing discoveries await you.
Thanks for joining us on this deep dive into the Stern-Brocot tree. We hope you found it as fascinating as we did. Until next time, keep exploring the beautiful and intricate world of mathematics.